So today we'll be going over the difference of naive SVM laws and the vectorized version. So hopefully going through a numerical example makes it clearer for people. So I'll put a link in the description about SVM laws in general. But our goal here is to look at this loss function and then take the gradient with respect to our w's. And we can adjust our w that way for the next iteration. So one key thing to look at it here is our value can either be 0 or a culmination of this expression here. And when we take the gradient with respect to w, here we'll still get 0, and then here we'll just get our x, which is the sample input. And specifically, x impacts the class we're looking at, and it also impacts the actual class of a sample. So I'll show what that means. So here we have our x. It's just 2 samples and 5 features, and it results in our margin matrix, which gives us the scores for each class. So we have class 0, 1, 2. And then over here we have the actual classes of each sample. So why don't we start with sample 1. So for sample 1, we'll just iterate through each of the margin scores. So here we have a positive score for class 0. So what that means is we'll take this x input vector and then adjust the column. So this is the class corresponding to this score here. And so we can just paste that in. Transpose. And what we have to keep in mind is each time we have a positive score, not only does it impact the class we're looking at here, which is class 0, but it also impacts, as we found here, the weights related to the actual class. So actual class is class 1. So that's this column here. Specifically, when we take the gradient, it's actually going to be negative xi. So what we'll do is paste in the negative. And then same thing here, positive. So we update this one. And then once again, we subtract from the actual class column here. So there we go. So that is the first sample. We can move on to the next sample after we paste these values in. So the next sample over here, we'll just copy that. And now we go through each of the margin scores. So we have 0 because we only do this loss function for the scores for the non-classes. So 0 is the actual class, so we don't care. Here we have another positive. So we adjust the class we're looking at. So that's the class 1 score. So we want to adjust the column associated with that. Paste special. And then we want to add. We don't want to subtract. There we go. And as usual, we adjust the actual class column as well. And then finally, on the last class score, we have 0. So there's no gradient changes necessary. So this is our naive version. And the intuition behind each of these scores is this is the impact of the feature on that class. So this is the impact of feature 2 on class 0. This is the impact of feature 2 on class 1, and then so on and so forth. So one idea here is instead of looping through the samples, we can actually loop through each of the features. So these features here, we can loop through them, and that lets us leverage the vectorization. So here we have x transposed, and then we have the adjusted margin. So what I did was each positive score I just changed to a 1, and then the actual class here, so 1, this cell will be a sum of the positives in that specific row. So if we have 1 and 1 here, sum to 2, so we'll have -2 here. And then over here we just have 1 and 0, so it's just a -1. So now what we can do is compute each of these cells using a dot product of this vector and then this vector, and then loop through each of these vectors. Essentially, this is just matrix multiplication. You go through each row, go through all the columns here. So what I'll do here is just do, and then here I can input the two matrices. And now we see we have the exact same gradient calculation, but instead we were just able to do matrix multiplication instead of looping through all the samples.